Hey, we made it, the definite integral. We're actually going to start saying the word integral instead of antiderivative and Riemann sums and add the area of the rectangles under the curve. Now we're going to lead into actually getting a formula and looking and seeing the weird new symbol that we have. So this one is all about our definitions and our theorems. There's not really any practice problems in here, but this kind of tells you what's happening. I mean, if you want to blindly just do problems and never have a clue, so when I ask you a word problem or your Calc 2 teacher asks you a word problem, you have no freaking clue what's happening, then just skip this one. Go on to the next. But this is going to be the one that's going to explain to you what's going on. We're going to get into the technical. We're going to get into the, oh my gosh, wait till you see this first one. Let's stop talking about it. Let's just do it. Let's look. The definition of the definite integral. And holy moly, look at all these freaking words. Let's dive into it. So if f is a function, all right, you got some function. Oh, maybe it's x squared. Maybe it's the cube root. I don't know what it is. And we say that our x is defined, including our endpoints between a and b, right? The interval, a to b. And we're going to divide it into n subintervals of equal width. Hey, you remember this? The change in x is equal to b minus a divided by however many times you're going to cut it into pieces. Yeah. And then we're going to have our little numbers, right? Remember those are our x naught, that first one, that's a, and then x sub n, that's b. Those are the last ones. Then we got a bunch of freaking numbers in between. So the x naught and the x sub n be the endpoints of the subintervals. All right. Oh, cool. Actually, misspoke that, but whatever. We'll keep moving forward. And then we have x sub I star, x sub 2 star. Don't stress about those sample points. We'll talk about that in a little bit. You just have to know that when you see that star, you're like, nah, shit, all right. Doesn't mean much. I just got to write them in. Unless you're a math major, just write the stupid things in where you're supposed to, and we'll move forward. I'll explain a little bit more in a second. So, x sub I star is in the ith interval, and that just means any interval, like the 7th or the 8th or the, but it's just one particular one. You don't know what it is. So we say that that x sub I star lies between x sub I minus 1 and x sub I. I'll show you in another picture. But all right, there's all the freaking words. Whatever. We're trying to, remember that Riemann sum bullshit we were trying to do, find the area under the curves? Well, let's look at it right to left. We're like, hey, there it is. That's the area of each individual rectangle. All of them. The area of each of these rectangles. This is our, what's this? This is our height times our width. And then this sum says, add up all of your freaking rectangles. And then this part here, this limit as n goes to infinity, says make all of those rectangles infinitesimally thin, no width. So we have infinitely many rectangles. And when we say that that happens, then our big conclusion happens. We're like, this is our new symbol. There it is. That's our new symbol. That's that shit we're going to be writing in good with that little summa from a to b of some f of x. And then we write this little dx at the end. It's like this change in x turns into this little differential of x. So that triangle of x, the change in x, delta x, whatever the hell you want to call it, it turns into that dx. When that change in x is so infinitesimally small, it's going towards 0. We call that thing dx. Okay, keep going. We'll say provided the limit exists and gives the same values for all possible choices of sample points. If it does not exist, we say, if it does exist, does, not does not. If it does exist, we say that f is integrable on a to b. All right, whatever, keep going. We'll see this again. This is our new friend. This is our buddy. This is what we're messing with. No more sums. We start doing the integration. Now we're into Calc 2. Now we're talking about the integral calculus. So let's see the difference between the two. Now here's our Riemann sum, right? Which just tells you to add up all your frickin' rectangles with each of those widths being delta x. Now let's explain the x sub I star, the sample point. Now where that is, as we jump into this, let's see if I can get my surface to work. There it goes. This point right here is x sub I. This line right there is x sub I minus 1. Our sample point just says it lies somewhere in between x sub I minus 1 and x sub I. So if we wanted to say, well, x sub 7 star, well shoot, that would be less than x sub 7 and x sub 6. Sitting somewhere in between. But whatever, it doesn't really matter. It doesn't really matter. Unless you're a math major, let's just move right past that shit. It's just this little star we throw on shit. All right, so that's our sample point. I'm going to get rid of all that stuff. And boom, when we got our sum, we're adding up frickin' rectangles. But when we actually do the integration and we have infinitely many, once we do our integration, we have infinitely many, we now say there's the exact area underneath the curve from some point A to some point B. There it is. Integration. We'll talk about it a few times. Hopefully this is just getting beaten into your head now. Here's our first theorem. If f is continuous. All right. For integration, we just need shit to be freaking continuous. Because it's going to be very challenging for us to try and find the area of something where it's like, here's our, there you go. Now find the area underneath those points. What the hell are you even talking about, area under points? But all of a sudden we make it smooth and continuous and we go from some point A to some point B and I ask you for the area. And you're like, well, no shit, I can find some area underneath there. So it's got to be continuous on the closed interval from A to B. Or, this is the weird thing, has only a finite number of jump discontinuities. We'll talk about that. Then f is integrable on A to B. That is, the integral exists. And that little jump discontinuity thing just means this. You remember our step function? Remember this stuff? Oops, hole. Remember this shit? Well, we could find area underneath this, couldn't we? A finite amount. We could find our little areas. I think I actually know I'm making my holes on the wrong side, but it doesn't really make much difference. A finite amount of discontinuities would be all right. Now, if there's infinite, we wouldn't be able to solve it. But really, I want you to catch this from it. Dude, if f is continuous on a closed interval, you can find the area under the curve. It doesn't mean everything's integrable. It just means that you can. That means the integral will exist, or if it has a finite amount of jump discontinuities. All right, here's our last one, the last theorem. If you're making it through, if you can make it a whole 10 minutes through this bullshit, maybe it'll make sense, maybe it won't. I don't know. If f is integrable on the closed interval from A to B, then the integral, this is what we're saying, the integral from A to B of f of x dx, that little dx, just this thing, is equal to this bullshit. Remember that first thing? That's true where, now look down here, at delta x, we already had that. Our delta x is equal to b minus a over n. And then our x sub I is equal to that a plus I. Change in x, right? These two things that we learned from before. We're just basically saying all the shit you did before, we're going to now change it, and we're going to call it integration. No longer will we take the limit as n goes to infinity. We won't have to make all the rectangles. We're going to be able to bypass this. So in your Calc 2 class, you probably won't have to do this part, but you're going to have to understand what it means, and you're going to need to know what the notation says. Getting used to seeing this right here. You got to be ready for that. This is huge, to be able to understand that this is the definition of the integral. So if you can just, how about that? Your homework for this slide, this video, not slide. Get that down. Notice the limit is n tends to infinity from I equals 1 all the way up to n of our sum of f of x sub I, and you're changing x. And you can put a little star in there if you wanted to, but it doesn't really make any freaking difference. All right, well, there it is. Kept it under 9 minutes. This isn't going to be so bad. I know it's dense. It's technical. Not a lot of stuff that we're typically, you can solve problems. But we'll get into it next time. We'll do some problems next time. We'll have some example stuff. See you then.